Good afternoon, everyone. I'm Pierpaolo Modugno from Queen Mary University of London, and I'm going to present my work on the influence of reaction parameters on the hydrothermal sugar conversion. So, before talking about my project, I'm going to give a little bit of context, although Frederick already gave more detail. So, we want to move on from an open carbon cycles, which is based on fuel fossil and cause the fossil fuels depletion and carbon dioxide accumulation in atmosphere. So we want to move from this system to a closed carbon cycle in which we use biomass to synthesize polymers and biofuels. And so we valorize bio-waste and we use renewable resources. So hydrothermal carbonization is a way to move to a closed carbon cycle. So hydrothermal carbonization is a conceptually simple process, and it allows to convert waste biomass into valuable platform chemicals and carbon materials by means of a simple hydrothermal treatment by using water in subcritical temperatures and autogenic pressure. In this way, we can synthesize chemicals such as hydroxymethyl furfural and levulinic acid, which are platform chemicals for the synthesis of biofuels and polymers. And also we can synthesize hydrothermal carbon, which has been used for catalysts, batteries, water treatment, and gas absorption. So let's see how hydroxymethyl furfural is synthesized. So cellulose in hydrothermal condition is hydrolyzed to glucose. Glucose is isomerized to fructose, and fructose is dehydrated to hydroxymethyl furfural. In a similar way, xylose, which is a constituent of hemicellulose, is dehydrated to furfural. Hydroxymethyl furfural in hydrothermal condition can furtherly react to give levulinic acid by losing a carbon atom in the form of formic acid. Hydrothermal carbon is the result of polymerization of hydroxymethyl furfural, and this is how it looks in a macroscopic view and microscopic view. So it looks like it is a powder and it's made of carbon spheres. So the aim of my study is to study the influence of reaction parameters on the hydrothermal conversion of sugars, the chemistry and morphology of hydrothermal carbon, and to have a look at the interplay between dissolved chemicals and hydrothermal carbon in the reaction medium. So my work consisted in preparing 10% weight solution of fructose, glucose, and xylose in water, subjecting this solution to hydrothermal treatment at 200 degrees in different conditions of pH and reaction time and pressure, and then collecting the products. So the liquid phase was analyzed via HPLC, and the solid phase was characterized by SEM, NMR, FTIR, and MALDI mass spec. So first part of my work is the influence of acids and reaction time on the conversion of simple sugars from the point of view of the liquid phase. I used a batch unstirred reactor. The precursor were fructose, glucose, and xylose. The condition were 200 degrees and the reaction time from 3 to 12 hours. The condition in acid catalyst reaction were 3 hours with a starting pH of 1.5, and we used as acid catalyst nitric acid, sulfuric acid, hydrochloric, hydrobromic, and hydroiodic acid. And the sample was prepared by filtration or centrifugation, and then the liquid phase was analyzed through HPLC. So in the first slide, we see the conversion products of fructose. The first thing we notice is that the complete conversion of fructose is very fast. It's already achieved after 6 hours, so it's relatively fast. And therefore, a high concentration of hydroxymethyl furfural is already reached at early stages of the reaction. And after that, the concentration of HMF, which we can see in orange, declines in favor of other chemicals such as levulinic acid, formic acid, and hydrothermal carbon. Here we can see the product of glucose conversion. The glucose conversion appears to be significantly lower compared to fructose conversion, and HMF, always in orange, in this case, it doesn't have the time to build up in the reaction medium, and it is as soon as it is converted, it is formed, it is converted to levulinic acid, formic acid, and hydrothermal carbon. So xylose conversion products are shown here, and we can see that the conversion is xylose is quite as low as glucose conversion, but in turn, obviously furfural is synthesized instead of hydroxymethyl furfural, and furfural appears to be furfural consumption appears to be slower compared to hydroxymethyl furfural. So furfural has the time to build up in the reaction medium. And at longer reaction time, little amounts of formic acid and acetic acid are formed. Here we can see the product of glucose and fructose conversion in an acidic medium. So in this condition, we can see that the glucose conversion is still lower than the fructose, and the nature of the acid has no big impact on the conversion of fructose, and all the yields of product are roughly the same in fructose, whereas in glucose we see that the nature of the acid has an effect on the conversion of glucose. And in general, we can say that harsher conditions push the reaction towards alternatively levulinic acid synthesis or hydrothermal carbon, and both on the expense of hydroxymethyl furfural. So the second part of my work focuses on the influence of pressure and feed gas on the conversion of fructose and glucose from the point of view of the liquid phase. So for these experiments, I used a batch stir reactor. The precursor that I used were fructose and glucose. The condition were I heated up my reactor to 200 degrees, and then the temperature was kept for 1 hour. No catalyst was used, and the reaction was stirred. The feed gas were alternatively air or carbon dioxide, and I used two levels of starting pressure: atmospheric pressure and 2 bar. So in this first graph, we see the conversion products of fructose in this condition, and we see so first of all, the conversion of fructose is quantitative, and we can say that a higher pressure has a slightly positive effect on fructose conversion, and conversion is improved by the carbon dioxide atmosphere. On the contrary, the glucose conversion in this condition ranges between 81 and 86%. So we can still see that a higher pressure has a slightly positive effect on the glucose conversion to soluble chemicals, but the presence of carbon dioxide atmosphere doesn't have a strong effect on the conversion of glucose. The third part of my work revolves around the influence of acid and reaction time on the conversion of simple sugars from the point of view of the hydrothermal carbon. So first, I'm showing the SEM pictures of the hydrothermal carbon samples that I prepared. So here are shown the fructose-derived hydrothermal carbon, and we can see that the carbon spheres are fused into each other, and the average diameter grows as the reaction time increases from 1.8 micrometer to from 0.8 micrometer to 1.7 micrometer. And also we can see that as the reaction proceeds, there is 2 population of particle growing. So for glucose-derived hydrothermal carbon, we see that the average diameter is much smaller at the same reaction time, but still, as the reaction time proceeds, we see that the particles have a tendency to fuse into each other. Xylose, on the contrary, doesn't have this tendency to fuse into each other as the reaction proceeds. So we see that the carbon particles grow in diameter at longer reaction time, but they still remain relatively with a spherical shape. As for the hydrothermal carbon obtained in acidic condition, we can say that the diameter is much larger. It is larger than 5 micrometers. So the acidic condition affect the size of the particles. We studied the chemical structure of these materials through NMR, through solid-state carbon NMR. So in this NMR spectra, we can distinguish 3 areas. The first area is highlighted in red and belongs to aliphatic carbon. And we see that there is an evolution as the reaction proceeds. So we see that there are 3 peaks in the early samples, and then there are 2 peaks in the longer reaction. This means that the aliphatic region of this material evolves as the reaction gets longer. So then there is the aromatic and unsaturated carbon area, in which we can distinguish 3 main peaks that can be identified as free carbon beta, linked carbon beta, and linked carbon alpha. This is relative to the structure of the furan, which is showed in the slide. And as we can see that as the reaction time proceeds, we see that the signal of the linked carbon beta becomes more relevant. And this means that there is a cross-linking in our structure as the reaction time increases. And then there is the carboxylic, aldehydic, and ketone area, and we see that there is no big evolution in this part. We can say the same for the solid-state carbon NMR of glucose-derived hydrothermal carbon. And the xylose-derived hydrothermal carbon exhibit the same behavior, more or less, but with some slightly different signals. So we can skip the FTIR because it just shows that we have a polyphenols.
I cannot see the presentation. I don't know what happened.
Oh, I don't know. I didn't do anything.
No, it's okay.
I'm going to, okay. So the FTIR spectra of this material shows that we have a polyfuranic structure, and this structure changes over time. So we go to a more condensed structure where we don't see anymore the stretching of the C double bond O due to aldehydic group. And also we can see a change in the vinyl group. Same behavior for the glucose-derived hydrothermal carbon. And the xylose hydrothermal carbon more or less exhibit the same behavior, but of course, we can distinguish in the spectra some spectral differences that are due to the fact, of course, that hydrothermal carbon is based on furfural units and not hydroxymethyl furfural units. The acid hydrothermal carbon shows that the acid doesn't have a strong effect on the structure, so the hydrothermal carbon obtained in this condition have more or less the same structure. So finally, we performed mass spectra mass spectrometry of this material by dissolving the material in tetrahydrofuran and then analyzing through Malditov. Of course, the material was just partially dissolved, but we can say, but from the mass spectra that we found, we found that there are some signals that are equally spaced with a spacing of 211 m over z. So this means that there is a monomer that condenses to produce different oligomers, and this monomer has a mass of 211 Dalton. So if we assume a reaction that is based on the condensation with a loss of a water molecule, we can hypothesize a mass for this monomer of 229 Dalton. So I made these two hypotheses. The first is the condensation of two hydroxymethyl-4,4 molecule, and the second is the aldolic condensation of a levulinic acid molecule with hydroxymethyl-4,4. So the masses of these two supposed monomers is quite similar to the one that we found, but doesn't match exactly. So this means that, so this can be an hypothesis, but we need further investigation on this part. So the
Pierpaolo.
yes.
Conclusions.
Okay, yeah. So we also found the evidence of the presence of glucose glucose oligomers. And so the take-home message is that the lower synthesis pH and longer reaction time push the conversion of exosis and pentosis towards soluble dehydration products and hydrothermal carbon. Pressurization of the system has a slightly positive impact on the conversion. Fructose and glucose-derived hydrothermal carbon share a similar chemical structure, whereas xylose-derived hydrothermal carbon shows some difference in the chemistry. Hydrothermal carbon chemical structure and shape changes over time as for long reaction, and we have evidence of cross-polymerization. And finally, the growth of hydrothermal carbon particles occur through aggregation of small oligomeric units. I would like to thank all these people for helping with my project, and thank you for your attention.
Thank you very much, Pierpaolo.
Thank you.
So we can open the Q&A session if there are any questions about it. Just 3 minutes. Yes, okay. Jan is writing something.
Okay, let's wait.
Jan is writing something, so
Yes.
okay.
So Joan is asking, what do you think about the extrapolation of your results for lignocellulosic material? Well, I didn't show any results on this lignocellulosic material, but I've worked, I did some preliminary work on some lignocellulosic material, and I would say that, so first of all, lignocellulosic material has lignin in it, and lignin is well known to hinder the hydrolyzation of cellulose. So I would say that, of course, I mean, that is an additional step in the synthesis of the material that I've shown. So I would say that the lignocellulosic material would be much slower compared to the material that I've shown.
Okay, thank you, Pierpaolo. Jan is writing something else? Or no? No, maybe you. Thank you. Okay, so we can conclude this oral session. One? She is writing something. Yes, you're right. Thank you, Pierpaolo. Okay.
What causes the shape of hydrochar to be different? I think this is I think this is caused by the fact that the chemical properties of the hydrothermal carbon is slightly different. So hydrothermal carbon formed from fructose and glucose is based on hydroxymethyl whereas xylose is based on furfural unit. And we don't have an exact explanation, but we know that the chemistry of glucose and xylose, hydrothermal carbon, are different. So they are slightly different, and this is caused by obviously by the difference in the base molecule, which is furfural or hydroxymethyl furfural.
Okay, thank you, Pierpaolo.